A bit later than advertised, but due to slight technical hitches, we're there. We've sorted things out. Now, what we're going to try is to look at some mass spectrometry and infrared spectrometry today and see if we can understand how they work and what we can actually get from them. So let's have a look at, first of all, what is mass spectrometry. And normally what we would have is a device feeding in stuff to a mass spec, and this is normally a gas chromatography setup, a gas chromatogram. This is then going to put the items into a little chamber, and in this little chamber basically we're going to ionize the substance that we put in there. So my substance X here is going to be ionized, and what it's going to do, it's going to come out of here down a little tube, and it's going to be accelerated by some little plates which are charged, and these particles are going to go through. Some of them are just going to hit and not get through, but others will go through. Then we've got a nice little bend in the system, and here we've got two enormous magnets, and these are controllable magnets, and so as we increase the charge here, this, if it's a heavy item, it's going to smash into the wall, and the lighter items are going to be deflected more onto a detector. As I change this, then the heavier items will also be bent round and the lighter ones will crash in here. So gradually we can, by changing here the field strength, different ions can be brought onto the detector, and this gives us easily, so we can work out mass to charge ratio. So what we want to do then is to look at what we're playing with. Now, some facts here that give us some ideas about how a mass spectrometer works. We are knocking off electrons, but the mass of an electron is, well, is virtually zero from the point of view here, and so the molecular ion here will have a molecular mass equal to the relative molecular mass of the compound. And what we're going to do is we're going to smash in here our item, which has to be in gaseous form. We're going to smash it to bits, and all these bits are going to be fired at the detector, and so what we get is an image that looks remarkably like something like this. So our item has been broken up into smaller bits, and we get different peaks, and the height of the peak is going to indicate the amount that we've got. So we can play around and analyze this mass spectrum and see if we can work out what we've got. So let's take a substance that we know and have a look and see what happens to it. So let's take something like ethanol. So we've got here a CH3, we've got a CH2, and we've got an OH. And what I'm going to do is basically we can smash this somewhere. Now, where is it going to smash? Well, the answer is everywhere, and I'm going to manage to lop off that. I might break there, I might break there, I'm going to break anywhere. And so we're going to get a whole series of different groups hitting this. So we need to know some numbers. So let's look at groups like perhaps CH2. We might look at groups like CH3. We might look for things like OH. We might look for things like CH2, OH, all hitting this. So we've got our mass here of 12, so that's going to be 14. This one's going to be 15. The OH is going to be 9. And if we've got this one, it's going to be our 9 plus 14, which is going to give me 23. So we should get a few different ones that I can predict that we might get. We're going to get all sorts of different things coming in. We might get all types. So these are just some numbers that we could possibly look for and we could expect, but we will get others. So with our ethanol, if we're going to get this, we're going to get perhaps what we're going to have for ethanol. So that's going to be, this is going to be simply C2H5OH. So we're going to get here our 24 plus 5 plus oxygen, which is going to be 16. That's not going to work, is it? And plus 1, 17. That was going to be 16. That's going to be 17. So here I can work out that what we're going to get here is going to be about, I estimate, about 46. Let's have a look and see what we're going to get. So this is the mass spec of ethanol. We've got a large peak I can see at 31. I can see another large peak at 45. And possibly the next largest one is 29, 27. So here I've got some values that we can sort of try and pick up and see if we can work out what we've got of, so we can do some calculations here. So I've got 31. What might make up 31? So this is where we have to start looking at what we can actually do to get some of these. So if we look at what we've got here, this is 45. That would suggest to me that's going to be CH3, CH2, O. We probably lost something there. If we look at here 31, it's not going to be those two added together. I expected to see something else there, but okay. So 31, let me think, what's 31 going to be? So 31 could be something like well, we've got CH2OH. I didn't add that up properly, did I? Because that's going to be 12 plus 3 plus 16, and as we see there, that's going to give me 25 and 16, that's going to give me 31. So that's going to be CH2OH and then we've got a 29. The 29 looks to me like these two, so that's going to be CH3, CH2, and I look here and I've got 27 as another high one, so that could even be CH3C as a sort of a thing that could have been knocked off. It's going to be all sorts of things, but let's go back and have a look. The highest number that I've got on here is my 46. Now I actually am getting something at 47, but it's a very minute amount. Now when we're looking at this substance, we're looking at carbon probably being carbon 12, but if I actually have carbon 13, this could sort of make a little bit of difference. And so we might expect carbon 13 if one of those atoms in my carbons here, if one of those were a carbon 13, then that would give me the value of 47, which is what we find. So we look at the major peaks to see what's happening. So I've got 46, which I can see. I've got 45, which is usually a hydrogen being removed. We've got then these 31's a big peak. We've got 29 as a big peak, and we will have some others. I've got 14, which I mentioned. We've got more of 15, the CH3. I've got a little bit of 17, I've got some 19, so very tiny amounts of some of these. We just go for the major ones. And so with this mass spec we can get some idea of what we've got. Now what we can do of course with this is the fact that if we take a known sample, ethanol, it's going to look like this. And what we can do of course is do our mass spec, compare it with this one, and see that if we get the same pattern, then we know it's ethanol. And usually most computers are tied in to these mass spec to give us these results. Let's look at a different one. So this here is quite different. We're seeing quite a different spectra for this, and here we're going to need to try and work out again what we've got. Some other numbers are coming up. They are numbers like 43. Now how can we get 43? Well, all we're doing is putting some of these things together to work out what we've got. So if I know that my CH3 here is going to give me 15, my CH2 is going to give me 14, then if I'm looking for numbers such as here 43, then how could I perhaps assemble this number? Well, could I have a CH3 and a CH2 and another CH2? That's going to give me for the carbons 36, and then we're going to get 43 here. So this is looking like a likely candidate to get the 43. We're looking at CH3, CH2, and that's going to give me, as we did before, that's going to give me not 31, 24 and 5. Yeah, okay, it's going to give me 29. So we've got that one. So I'd expect to see an amount of 29 on here, and if we go and have a look, I can see, yeah, I've got a small amount of 29, but 43 is my major one. Then let's go and have a look at the far end, because this normally gives me what we've got. So I'm looking down here at the maximum peak, and this maximum peak looks like it's at 72. So if we've got 72, then if I start putting my CH3, CH2 together, then we might find that we can get, for some of these, let's try 5, which is going to be C5 H12 if it's going to be pentane. So we could try having a look at that. So all we've got is 5 12s are 60, makes 72. So it's looking like this is possibly a pentane. And what's trying to help us there is we've got some numbers like perhaps 57. If I look in there, I can see I've got a peak at 57, and what might that be? Well, we can see that if we're trying to get 57, that might be a C4 with a number of H's, so that's going to give me a number of 48 plus what we want to try and put with some hydrogens to see what we've knocked off. So if we've just knocked off 3 hydrogens on there, that's going to give me 9, so that's going to give me 57, which is C4 here H9, in that we've knocked off that, and so 57 is there. And so I'm thinking that this is probably something like pentane. Well, a lot of these you've normally got some sort of idea of what chemical you've got to start with. If you haven't, then we need to use more than just mass spec to try and do this work, to try and help us. Let's look at another simple mass spec. This time, instead of looking at pentane, this is looking at 2-methyl butane. And 2-methyl butane coming up with a much more distinctive pattern. If you look at the same number of carbons, but we go back, unfortunately where they've done this, the numbers are moving around a little bit. It's not on the same sort of, quite the same scale, but we've got again 57 coming up as a large peak. So I'm thinking that when I start, that if I've got the 57, we're looking at C4H9 in there somewhere. We're looking at a large peak here of, lost my mouse, 43, and we know that was CH3, CH2, CH2, and some more bits lopped off that when it goes. I'd also be looking, if I've got this methyl, 2-methyl butane, we might be looking at some CH3 group in abundance, and so I might be looking at a large 15, and we're seeing that. So it gives us some hints about what we're looking for, although it doesn't sort of solve the problem entirely for us. We can get some other ones which are quite interesting. There's this one, for instance, and here we're trying to work out something we've got here, and we've got something massive at 31, and we know from our previous sort of working out 31 was in fact CH2OH. So if I had to make a guess, this substance is probably an alcohol. Now, what else can I get from this? So I know it's an alcohol, and that's that peak at 31 knocked off. Then here it's set at 60, so I've got a big group at 60, so it gives me an idea that we've got something like this at 60, and we can try and work out what we've got. So let's have a look and see what sort of things that we can get. So we've tried some of these things to work out, but we've got some special numbers we can start to remember. We've got 15, which is CH3, which is a plus anyway. We've got 17, which is an OH. We've got 29, which is a C2H5. We've got a 43, which is a C3H7. We've got the 57, which is our C4H9. So we've calculated those. We've got some of those coming out to work out, well, what could we have? So what we do when we look at our spectrum is we try to work out what we've actually got and to see what it's going to fit for these particular molecules. Now for this one I don't know what number 4 is, and I've got to try and guess what we've got. So I can look at number 4, looking at the screen, and I'm seeing that 60 is the highest number. So if I know that we're looking at 60, this is its probably its relative formula mass. So we're looking at something that makes up 60. Once we've got that, then we can look for a few other numbers that might try and help us. We've got some of those. I'll put a couple of other ones down that might help. We've got then our CH3, CH2O that comes in at around about 45. That one is also fairly helpful to try and work out what we might have. So that gives us some ideas of what we might have. Okay, so can we do any more work on this to try and determine what we've got? So we've got a 60, then usually we get a 59, that's something with a hydrogen dropped off. I've got a little 43, we've got a bigger 42, and we do have this massive spike at 31. So the 31 is fairly indicative of a CH2 OH group. So we're looking here at some sort, I would have thought, of alcohol, and then we've got some other numbers. I can see 29 there. We've got the 27 again. So we've got probably a straight chain here, and we've probably got some sort of alcohol to try and work that one out, and then we can work out all the numbers. Looking at another one, here we've got a different one. So this is again much heavier. This is looking at about 70. So this one with its 42, that's not fitting nicely with an alkene, but we haven't got an OH group. So we've got something large at 55. Now this is giving me a hint that we haven't got any at 31, so it doesn't look like an alcohol at all. I've still got my large 29s, got my 27s, so that's all fitting there. So this is looking like some sort of straight alkane, but it's not fitting with 70, and it's not fitting with 55. So whereas with this one at 60 I worked out it was quite happily an alcohol, and just going through my alcohols working out what it was, I can actually work out quite happily what that is. This one is shoved up at around about this time. We've got 70. Now 70 is giving me an idea that this has got to be a C5 carbon. We know it's not an alcohol, so it could be instead an alkene, and that would fit with what double bonds we've got and the numbers of carbons, because my carbons were lower than I was expecting. So this one is in fact pent 1ene, but had I chosen pent 2ene, there's very little difference we'd really see on a mass spec. There will be some. We're going to see a similar fragmentation pattern, but you would see different peaks on some of these. Going back to the previous one, which I didn't solve for you, this is a 60 carbon. Now, to be a 60 carbon with an alcohol, I know I've got 16. I'm going to have to put in here, let's say 3 12s, that's 36, and once I've got my 36 in there, that's going to give me about 52. With the hydrogens there, this has got to give me something like propanol, because it's the only thing that's going to fit in with what we've got. So mass spec, it's a lot of looking through numbers, trying to work out combinations to try and help you, but it's not the only tool that you've got. And we do have some other tools at our disposal which can help us. And if we then have a look at some infrared spectroscopy, then this can give us some ideas about how we can sort of make some things work together. So let's go off and now have a look at infrared spectroscopy, and then we can combine the two techniques to get us an answer. Now, how does infrared spectroscopy work? Well, basically you shine infrared light at a substance, and at certain frequencies it absorbs that light, and we can look and see how that light is absorbed, and certain molecular movements do things. And for this I really wished I actually had some models that do this, but unfortunately I don't have models that will do this. I can have two molecules here that are joined, and that bond can stretch, or it can contract. We can have another type of bond where something here, they may move up and back, they can sort of wiggle, they can do a bit of rotation, they can spring in and out, and they can either do those in and outs together or not. And I'm now going to make a fool of myself, and I'm going to try and do some of those and show you. Right, so what I'm going to do is I'm going to put the camera on me, and I didn't quite get it centered on me because I did it without looking. Paul's going to pull the camera around a bit for me. That's it, lovely. And I'm going to pretend my head is an oxygen atom and my hands are the hydrogens. And they can do rather daft things. And usually when I try and do this, I try not to make too much of a fool of myself, because I normally get the class to stand up and they have a go at doing that. So I'm going to stand up, and Paul's going to track the camera with me, and we're going to have a go. Right, okay, so he's going to zoom out so we can see my hands. Right, so I'm a water molecule, hydrogen, and then we've got, oxygen, hydrogen, hydrogen. And these bonds can go up and down. They can go in and out. They can go round. Yeah, I think I've made enough of a fool of myself for that one. So we can look at what sort of things, movements these molecules are going to take, and they're going to absorb different amounts of energy to do these different movements. So we send in infrared light. Now this means we've got to put our stuff that we're measuring in a suitable container, and an infrared spectrometer looks, wrong button, amazingly like this. We have my infrared light, we have my sample case, which is called a cuvette normally, and we have a detector. When I did this, when I worked in a university, we had really what you would determine now to be pretty ancient devices. Big things that we could not really move. They were sort of transportable if you had something like a forklift truck. But nowadays these things really are quite small. and we can manage to sort of move these things around very easily. So we're going to send some infrared light through a substance, and we're going to see what happens when we put it through a substance. And here I've got a substance, and we're putting infrared light through, and we can see that it's absorbing at certain frequencies. Now, some of these mean something, and some of them are really hard to work out. Right, sorry about that. Right, okay, so let's see what we've got. So I've got this massive peak here. This is probably the most indicative peak that we've got, and we've numbered what they are here. So this is at 1710, and if I've got a suitable book with a suitable set of numbers to have a look at, then what we can do is we can get some idea of the figures for this. So this is just a chemistry book, and it comes with a whole series of wave numbers, what the location of the item's going to be, and probably what the bond is going to be. So I've got a peak at 1710, and 1710 is around about there. I've got possibly a C double bond O, and this is the sort of thing that I'd find in an aldehyde, a ketone, carboxylic acid, ester, amide, acyl chloride, or acid anhydride. So I'm looking at something like that in here. Right, let's see what other peaks that we've got. Well, the next biggest peak is at 1220. Now, 1220 doesn't help me an awful lot, but we can have a look at what we might have for 1220. Looking at my list for around about 1220, then it's suggesting that possibly things that I might have are a CF or a CO bond. Now, I happen to know this substance doesn't have any fluorocarbons in there, so I can actually discount that one. So we're looking at something that's probably got a CO in it. 13, next one on my list, is I've got another peak at 1358, and 1358 is again not terribly helpful, because it's not really in my range, so not much help there. Sometimes looking at this tells us what we haven't got. So if I look between 3200 and 3600, we can see that we don't have an alcohol group. So I know I've got something in the C double bond O region, but it's not an alcohol. It also, we don't seem to have much in the way of an amide, because that would be at 3,4. Now I do have a tiniest peak at that. Now, what might that be? Could be a contaminant. You never know. I've got one at 3004. 3004 is looking very likely to be a carbon hydrogen. So we've got here, probably that. And if we look down the end of the system, we've got sometimes this part down here, which we tend to call more of a fingerprint region. So this is giving me some things that I know that we might have. Now, if I'd done some mass spectrometry with this, I'd also have an idea of its relative formula mass. And once I've got my relative formula mass, and I can determine that I've got a C double bond O group in there, and it's not with a CO, it's not a carboxylic acid, so we know we've got a C double bond O, then we're looking at something that could be either an aldehyde or a ketone. And the position of this, again, the fingerprint of this tells us that we've actually got a ketone, and this in fact is acetonal propanone. Let's look at another one. So we're going to look at our tables, let's see what we've got. And this is a very different spectrum that we've got. I've got a massive peak here at 1045. 1045 is corresponding with either a fluoroalkane or an alcohol ester and carboxylic acid. Okay, we've got another massive peak over the other side, a really wide one at 3316, centered around that, and this one, here we are, 3316, you can see where it is. 3316 then corresponds to probably an alcohol. If it's a carboxylic acid, I've got one at 25. Well, 25 seems to be missing, so it's probably not a carboxylic acid because there isn't a broad peak there. It doesn't appear then likely that it's an amine, so it's probably an alcohol. What other ones have we got to try and help us here? I know I've got an alcohol, and we've got this very interesting and specific fingerprint down here which can help us to try and identify. I've got some round here, some carbon bonds, probably that one, and I've got some other ones up here which are nothing really specific, but it's around about this region that we see are alcohols, which is what we've got there. So I'm going to guess this is an alcohol, and in fact this one is, as you can see up there, this is actually ethanol. If we look at another one, this time we've got ethyl acetate. Ethyl acetate is quite a different kettle of fish. This here is an ester, and this one's going to give us some interesting problems when we try and have a look at this one. We've got here some ideas about what we've got, so let's look at what peaks we can pick up. Well, we've got this massive peak, 1233, 1736. 1233 is right in the middle of alcohol esters and carboxylic acid, so that fits. We've got the C double bond O between 1600 and 1800, and there it is here at 1736, so that's suggesting we've also got here something which is an ester as well, or carboxylic acid. We've got one at 1372 and 1043. That might suggest we've actually got here more on this ester or alcohol, and 1372 not labelled in this one. And so with help from our mass spec, help from the fact that we can look at some of these and not have particular things, I've got something about 2.9, 2.9, a fairly broad peak, which is what we've got, is reminiscent here of a carboxylic acid, and we've got something like that because this, in fact, as we said, is ethyl acetate, and with the mass spec that would help us. To look at the last one on this list, we're going to look at toluene, and toluene, again, a completely different fingerprint. So these are quite easy to sort of work out what we've got, because we could compare this with a known and it's very easy to work out. We've got here some sort of alkyl alkane chain. Down here we've got these numbers. We've got, for the arenes, the C double bond O, sorry, the C double bond C peaks in 1400 range, and there we've got that one. So it comes in here, giving me a hint, several peaks around about here for the arenes, several peaks here visible in that range. So we've got here for the infrared some other help which we can put with the mass spectrometry data, so we can start working out what we've got. So infrared by itself doesn't really help. Infrared tells us something about the substance. It tells us that we may have an OH group, a C double bond O group. We might have a CN group. So we've got those. We use then the mass spec to have a look at what we've got, and we can also get a fingerprint from that. And either we shove it into the computer, or unfortunately if you're trying to do this in an exam, they'll give you infrared data and they'll give you mass spec data. So where do you start from? Well, let's have a look at those two simultaneously and have a look and see what we're going to work out. So what I've got is, going back here, having lost my mouse, there we are, this is my ethanol, the first one we looked at, and what I can say from this very happily is that it's got a number 46. So I know I've got 46. I know we've got a peak at 31. So from that I can guess that I've got possibly an alcohol that is that number, that is 46. I can then, looking at the infrared, determine that this is indeed an alcohol group. We've got information in here that leads me to know that it's definitely an alcohol, this wide peak here, this one here. So I then know I've got an alcohol I'm looking at. I've got an idea of the mass. I've got an idea of some of the groups that might have come off of it by looking at the mass spec. And by using both of those, we can put the data together and we can work out what we've got. So that wasn't easy, but it's not also that hard, because the substances you'll get given won't be that difficult really. What you will have, however, is later some NMR. Now, as soon as we come on to NMR, we meet two sorts of NMR. We come across carbon NMR and hydrogen NMR. And although they're the same, they're actually different. Now, when I went to university, we did have an NMR machine. We were told we had an NMR machine. That was it. You weren't allowed to go and see it or anything. It was a small fortune. Whereas my son, who's done his chemistry degree, has not only done NMR, he's actually taken out a portable NMR around the country and taken it into schools and taught other students about how NMR works. And in addition to the NMR, we've got the mass spec, and I'd love a mass spectrometry machine. I really would. Just waiting for someone to offer to lend me one, or better still, give me one. I don't know what I'd do with it, but I've always fancied one. So if we've got an NMR machine for either proton NMR or carbon NMR, we've got then infrared spectroscopy, mass spectroscopy, and then another one, UV spectroscopy, which works with certain substances. I want to try and show you a UV of alcohol. Now, it's extremely boring because it's just a straight line, because it doesn't absorb anything. And for the life of me, I can't find anyone who's actually done something. They don't like doing things that don't work. Because you do a UV spectroscopy of ethanol, it's just a straight line. It's a negative test. It says, well, look, it isn't any of these things. So next time, what we're going to have a look at is proton and carbon NMR. We'll have a look at ultraviolet spectroscopy. We'll put that together with mass spectrometry and infrared spectroscopy so that we can get an unknown item, and we can go through, we can explore and work out what it is by using all these analytical techniques to work out and identify a substance. Until then, stay safe. If you like what you saw, listen to, then please subscribe, and I will see you same time, perhaps a bit earlier if I don't have computer problems, next week. Take care. Bye bye.